At the beginning of the previous video, I showed you how we usually, or how we have been representing a point using x and y coordinates in a rectangular grid. And then I showed you how, by comparison, we can describe the same point by using a radius and an angle. In this video, we're going to look at the relationship between these two representations. I'll start by drawing a grid. And I'll go ahead and put that same point in about the right location. Just in case you're not quite following, this point, and this point are all supposed to be in about the same location. In this case, I'm describing it using x, y coordinates, rectangular coordinates. In this diagram, I'm representing it using r, theta coordinates. And in this diagram, I want to take a look at the relationship between those two. If I draw my radius from the polar coordinates and then drop a vertical line, this is the kind of diagram we've been working with. This is r, this is y, and this is x. I'm also going to label this angle here theta. Now we've seen this diagram before. This is how we described the trigonometric ratios, not right at the very beginning, but not too far into the course. Instead of just taking the sides of a triangle floating in space, we imposed a coordinate system on them and we started labeling the sides according to their lengths. This side here has a length of x because it starts at the origin and goes out x units. This side has a length of y because it starts at y equals 0, not at the origin, but at y equals 0, and goes up to a height of y. This side here we labeled r because we assumed that we could superimpose a circle on this diagram. Now the reason we did all of that is so that we could write, for example, that the sine of theta is equal to y over r. Multiplying both sides of that equation by r gives me r sine theta equals y. So one way that I can write y is as r sine theta. The cosine of the same angle theta is adjacent x over hypotenuse r. Multiplying both sides of that equation by r gives me r cosine theta equals x. So I can write x as r cosine theta. Now, this doesn't come as much of a surprise because we've already learned that x, y can be written as r cosine theta, r sine theta. That's not new. What is new is that I can use this way to represent a point, or specifically a way to represent x and y, as a way of converting between rectangular coordinates and polar coordinates, or actually in this case, converting between polar coordinates and rectangular coordinates. For example, if I give you a point in polar coordinates 3, pi over 6, that's my r, 3, and my theta is pi over 6. That's how we write coordinates in the polar coordinate system. If I want to convert that to rectangular coordinates, then all I have to do is write x, y, where x is r cosine theta and y is r sine theta. In this case, that's 3 cosine pi over 6, comma, 3 sine pi over 6. Now, I know what the sine and cosine of pi over 6 are, so that means I'm going to have 3 times cosine of pi over 6 is root 3 over 2, comma, 3, put a times in there, 3 times the sine of pi over 6 is 1/2. So in rectangular coordinates, this point is at 3 root 3 over 2, comma, 3 over 2. So these 2 points are equivalent, 3 pi over 6 and 3 root 3 over 2, comma, 3 over 2. Let's plot both of those, one in polar coordinates and one in rectangular coordinates, and see if they match up. I'll start by drawing a grid, and then let's graph the rectangular coordinates first. 3 root 3 over 2 is about 2.6. Let's see, I'm going to go 1, 2, 3. So I'm going to be starting about here. That's my x-coordinate. Remember, this is my r comma theta. This is r comma theta. And this one here is x comma y. Okay, so x comma y is going to be 3 root 3 over 2, which is about 2.6, and 3 halves is 1.5. So let's put that in there. 1.5 is going to be here. So that point will be right about there. This is 3 root 3 over 2, comma 3 halves. All right, now I'll use a yellow pen, and I'm going to try graphing 3 comma pi over 6. Let's see. First of all, pi over 6 is about there, and then my radius needs to be about 3. Well, this point here is 2.6. So that the length, it's hard to describe what's happening here. The length I've gone, the distance I've gone out in the x direction, that is 2.6. But the hypotenuse of this right triangle is going to be longer than that, right? So let's drop a vertical down there. I know the height of this leg as well because that's my y-coordinate. That is 1.5. This side is about 2.6. And using the Pythagorean theorem, this hypotenuse should be 3. So I'm going to say question mark squared equals 2.6 squared plus 1.5 squared. Now those are both rounded values. So when I do the arithmetic that I'm going to do just now, I'm going to use the much more accurate values than just 2.6. I'm using 2.598076221, just in case you're wondering. I just did the arithmetic 3 root 3 over 2 on my calculator, and it gave me that 2.5980, that number. That's the number I'm going to be using to square, and then I'm going to add 1.5 squared. That actually is the exact value there. So 1.5 squared, that gives me 8.9999, which is technically equal to 9, but we won't go into that in this environment. 8.999, it's giving me 8.9999 instead of 9, because even though I used 1, 2, 3, it looks like 10 decimal places for 2.6. It's actually, like I said, 2.598. It's 10 decimal places. This has accuracy to 10 decimal places. And even though I've used 10 decimal places, it's not the exact value. 3 root 3 over 2 is the exact value, and I've used the decimal approximation. Now I could, let's erase this. I could do it a slightly different way. I could say, instead of going and getting a decimal, I used a decimal to graph it. Right? I found a decimal 2.6 so that I could graph the coordinates here. But let's say, since I know that this 2.6 is an approximation, and the real value there is 3 root 3 over 2, that's my x. If I square that and add it to my y, just 3 halves squared, then take the square root of that, I should get this third side, right? The hypotenuse. Well, 3 root 3 over 2 squared is 27 over 4. I'm ultimately going to take the square root of this, plus 9 over 4. And sure enough, this is 36 over 4. And that is, the square root of that is 6 halves, which is 3. So I have used Cartesian coordinates or rectangular coordinates to plot this point initially. Then I checked that the 3 comma pi over 6 still worked. I went out the angle pi over 6. I went around to the angle pi over 6 and drew a line out. And then I went out that line 3 units. Well, actually I didn't. I just assumed that the point I had already drawn would be 3 units out. And what I've done down here is verify that that is in fact the case. So this is the relationship between polar coordinates and rectangular coordinates. If I give you a pair of coordinates, a coordinate pair in polar coordinates, you can convert those into rectangular coordinates using these two little formulas. Formulas that we are already familiar with, by the way. So what I've shown you so far is how to take a point given to you in polar coordinates and convert it into Cartesian coordinates or rectangular coordinates. I'd like to do another example, but then I'm going to show you how to take a point given to you in rectangular coordinates and convert it into polar coordinates. So on the next slide, I'll do another example of going in this direction first, and then we'll move on. Let's convert the point 6, 5 pi over 3 from polar coordinates into rectangular coordinates. I've put the formulas that we're going to need up here in the corner. And basically, what I have is r comma theta, and what I want is x comma y. The good news is that's just r cosine theta comma r sine theta. And I know both r and theta. So all that's left to do is figure out what the cosine of 5 pi over 3 is and the sine of 5 pi over 3 is, multiply those results by 6, and I've got my rectangular coordinates. The cosine of 5 pi over 3, I'm going to revert to that old standby coordinate system. This is 3 pi over 3. Another pi over 3 would be 4 pi over 3. Another one would be 5 pi over 3. So 5 pi over 3 is there. My reference angle, theta bar, is pi over 3. That's how big that angle is. So all I need to do is figure out what the sine and cosine of this angle are, and then make sure I have the right plus or minus. Now, the cosine, let's rewrite the 6. The cosine of pi over 3 is a half. And the sine of pi over 3 is the square root of 3 over 2. Now I'm going to check my sines. I'm in quadrant 4 here. That was pi over 3. My actual angle is 5 pi over 3, right? So because I'm actually in quadrant 4, this is just this reference angle is just the right size of angle. It doesn't deal with the sine. I'm in quadrant 4, and what's positive in quadrant 4 is cosine and secant. Cosine is positive in quadrant 4. That means cosine, this is going to be positive. Sine is only positive in 1 and 2. Sine is not positive in quadrant 4, so that means my root 3 over 2 is negative. So my coordinates are 6 times a half, which is 3, and negative 6 times a half, which is 3 times the square root of 3. So what I had in polar coordinates, I now have in rectangular coordinates. That's all there is to it. The nice thing is we can go the other way as well, although we have to be careful with those formulas. Let me start a new screen to do that. When we were converting from polar, r comma theta, into x comma y, rectangular, what I needed was a way to write x and a way to write y using r and theta. If I want to go from x comma y into r comma theta, then I need a way to write r and a way to write theta using x and y. So going in this direction, I started with r and theta. They're in my right-hand side here, and I used them to write x and y. So to go from r comma theta to x comma y, I used formulas that were set up for x equals and y equals. So what I'd really like is to have formulas for r equals and theta equals, and I can get those as well. Let's just do quadrant 1. I'm going to draw a generic angle, theta, drop a vertical. I'll call this x, this y, and this r. This is how we've been labeling triangles in the first quadrant for a while now. Can you think of a relationship that tells you what r is based on x and y? How about r squared equals x squared plus y squared? Okay, we usually say x squared plus y squared equals r squared, but it's the same thing. And then if I take the square root of both sides, I get r equals the square root of x squared plus y squared. Now, normally I'd say don't forget your plus or minus here, but because we're dealing with a radius, I know we've just been dealing with polar radii that can be negative, but we're thinking of this as the length of a side of a triangle, so that has to be positive. So r, if you know x and y, r can be found by plugging x and y into that formula. Now, can you think of a relationship about theta that depends on x and y? Think about the fact that this y here is the side opposite theta, and x is the side adjacent to theta. Does that help? How about the tangent of theta equals y over x? Now, technically, this doesn't tell us theta just by plugging in x and y, but we can do this. Theta equals tangent inverse of y over x. You'll actually see both versions of this in different textbooks. Your textbook actually gives this version as the way to obtain theta from x and y, but I'm going to write it down this way. Theta equals the inverse tangent of y over x. It's actually your choice, whichever one helps you remember. But if I write x comma y equals r cosine theta r sine theta, then I also like to write r comma theta equals root x squared plus y squared, that's my r, comma tan inverse y over x, that's my theta. Okay, let's do an example of one of these. If I give you 2 comma negative 2 in rectangular coordinates, can you convert that into polar coordinates? We have rectangular coordinates. We want r comma theta, where r is the square root of x squared plus y squared, and theta equals tan inverse of y over x. Well, that's r equals the square root of x squared plus y squared. Y squared is going to be 2 squared plus negative 2 squared. That's my r, comma, tan inverse of, what was my y? I've lost the point that I was working with. It's here. Tan inverse of negative 2 over 2. Of course, that's negative 1. The square root of 2 squared plus negative 2 squared is the square root of 4 plus 4, which is 8, and that's 2 root 2. The tangent inverse of negative 1, let's see. All students take calculus. The tangent is negative here and here. And in our case, our tangent is negative 1, so I'm going to have opposite over adjacent. Opposite and adjacent are both going to be 1. Actually, they're both going to be 2. Let's go ahead and label them 2 because that's how we got them. Opposite and adjacent are both 2, but they're negative, right? So the ratio is negative 1. The thing is, in quadrant 2, it's the adjacent that's negative, and in quadrant 4, it's the opposite that's negative. So which one is it? Well, I got this negative 1 by dividing y by x. So the y, looking at my diagram here, y is my opposite. I want the instance of this where the opposite is negative and the adjacent is positive. Here the opposite is positive and the adjacent is negative. So I don't want that version, I want this version. Now, because the opposite and the adjacent are the same, at least in terms of their lengths, this must be a 45-degree angle, or pi over 4. If the reference angle is pi over 4, then this is 7 pi over 4. This angle here is 7 pi over 4. So the tangent inverse of negative 1 is 7 pi over 4, or negative pi over 4, because we're in polar coordinates. I could also just take the size and say, well, I'm going to go backwards instead. All right, now you know what polar coordinates are. You know how to graph them, and you know how to find coordinates if I give you a point. You also know how to convert between polar coordinates and rectangular coordinates in both directions. In the next video, we're going to be taking a look at something called polar equations. If we know how to plot points in a polar coordinate system, we might as well do something with them. So we're going to be graphing some polar equations. We're also going to be doing some algebra on those polar equations.